I'm ready. Okay, but I want to make recording on my side too. So I'll turn on the recording. Okay, so finally we have 34 again. Okay, so today we will have a very controversial lecture. It is called Physics Horn of the Y-shaped diagram of mathematical physics. And as I explained, we will go in both ways. Somewhere we will meet and go together. Okay? Because it will be hard to understand what is going here without knowledge of these two horns. Okay, so I assume that most of audience are mathematicians, okay? So if you are a mathematician, so my first statement, you should hate physics at school. And actually, because it is completely illogical. So to be a mathematician, you have to have, it's a necessary condition, a perfect logic. And school physics, and then bachelor general physics is illogical. I mean that rules are changing every year. So it's like, I don't know, like something in the United States, it is just laws that are voted by Congress and signed by president. Each time they are telling you that now we add something or we exclude something or this was not quite right, etc. It's absolutely impossible to study physics in this way. However, there is a logic in physics. So, actually, what I'm going to tell you is the following. First, pre-classical physics. So this was discovered by Newton. So what I would like to tell you is that this pre-classical physics of Newton is A, not consistent. Only approximately describes our world. So there are many assumptions here that are just wrong. And I'll discuss non-consistency, of course. Then there is so-called classical physics. So what is interesting is that there are no books on classical physics. And I'll explain why. So classical physics is a physics of what? Of fields and extended objects, just like strings, particles, strings, membranes, etc. And there is no good book on classical physics. And then there is a quantum field theory. So actually, there were two revolutions in science. One revolution is like this, is going from classical physics to quantum field theory. Another revolution was a hidden revolution. It was going from pre-classical physics to classical physics. At the same time, what people study at school and on the bachelor program of the university is this. Especially mathematicians. That's why it's not hard to understand why they completely do not understand what mathematical physicists are talking about, because they're talking about this and sometimes about this. Okay? So, in order to get contact with the audience, I have to change the situation. Okay? So there is a blink here. Wait a moment. I'll try to do something about it. You see, I have a problem with the sun. Maybe I'll try to kill it this way. Okay, so people are still coming. Very good. Oh, people are going, are leaving. Oh, sorry, I have something in the chat. Yes, no. Okay. Very good. So, I will do some kind of correction today. Namely, I'll explain what happened in this pre-classical physics, why it's wrong in many ways, and how we should go to classical physics. Then, in the physical form, I'll briefly explain classical physics to the level that is needed for mathematical physics. And then I'll go to QFT. But before I'll do this, I'll try to explain the subject and the role of mathematical physics. So, mathematical physics, from my point of view, studies the worlds that are similar to our world in some aspect. So it studies not only one world, but actually many worlds. Let me give an example. Our world has dimension that is 3 plus 1. It means 3 space dimensions and 1 time dimension, roughly speaking. There are worlds that have more dimensions, and there are worlds that have less dimensions. Same. There are worlds that have 0 dimensions. Interesting worlds have, say, 1 plus 1, 2 plus 1. So idea of mathematical physics is to study all these worlds together. So somehow it is a base. And then what we are studying, what is the reason to study all these theories up d equals 10 plus 1? Say like 11-dimensional supergravity. Or even d equals 26. Why are we doing this? It is because we are studying worlds in order to study effects. As a function of the worlds. And typically behavior of the effect or phenomena is like this. Simple worlds sometimes have no phenomena, but then phenomena appears like this, and then it grows. Another phenomena goes like this, and then it grows. Now, in order to understand phenomena, we need to find the place where phenomena just appears, because at this place, this phenomena is most easy to study. Then we get from this study our understanding of phenomena, and we continue to the higher worlds. So people know this, say, in differential geometry. The simplest differential geometry is in dimension 2. It's very easy to study. It's very effective. You may say that we need differential geometry in dimension 3 plus 1, because here it describes general relativity. But we should not start from 3 plus 1. We should start from the place where phenomena appear, say in dimension 2. Get used to it, and only then we move to our world. So this business of studying effects or phenomena as the functions of the worlds is what people are studying. Actually, the dimension is only one parameter of the world. The space of worlds is multidimensional. Okay? In particular, classical worlds are just submanifold here. Say classical theories. Submanifold in the family of possible theories. So we study all these theories, we study this phenomenon. Okay.
So its dimension discrete, continuous.
So here I put dimension as discrete. Maybe at some moment people could study continuous dimension. I'm just not comfortable with it. So at the moment I understand dimension as discrete. To show you another parameter in the world, let us say the gauge, another direction of the base, the gauge group. You may consider something simple, U1. It's simpler than SU2. All the way down to the U1 times SU2 times SU3 times SO31. And this is the gauge group in Einstein-Cartan gravity. So these are different worlds. So it's not only gauge group that stands here, it's also, if you wish, matter content. So there are actually many theories around us. By the way, when we say gauge group, it could also be, there is the following generalization. Theory with the one form potential belongs to the theory that have p form potential. So there is another generalization, and so on. So this world is really big. So of course we will discuss this world, but before we will go here, I have to explain you how all this would be related to what you thought you know about physics. So today I will criticize Newton in many ways. Okay? So let me come to the point of Newton's laws. So main concept in Newton's theory is the notion of the body. He is not defining what the body is. However, we may assume that the body is something like solid body. Our guess. Then, what is interesting is that Newton attributes to the body the vector r that belongs to R3, called position. As you know, if we consider solid body, then it is given not by 3 numbers, but by 6 numbers, namely actually position, orientation. So orientation is SO3 torso. So this is for mathematicians. So physicists know what orientation is. But proper mathematical notion is SO3 torso. So depending on who you are, physicist or mathematician, you will understand what I mean. Then Newton says something about inertia. And when he is saying something about inertia, you see, I read his book in Russian translation. Then he is hand waving. And he is saying that somehow constant rotation. is inertia. So it means that he understands that orientation has to be put somewhere on his axioms, but then he ignores it. Moreover, when he says constant rotation, it is clear what it is for a sphere. However, what is a constant rotation for a body of some other shape? It's interesting. Because actually, now we know that instead of saying constant rotation, one has to say constant momentum. Constant angular momentum, sorry. But Newton doesn't know what angular momentum is. So that's why somehow here is his first fault. By the way, nobody corrected him. Okay. So actually, it is because he was applying his axioms to planets and stars. And if you look at planets and stars, there are spheres, and their motion could be described by most of their position. But people think or claim that these are axioms for any mechanical motion. So sorry. In this way, they are absolutely incomplete. Now, he says, axiom 0 or axiom 1. It is called the first law. There is a coordinate system such that without forces from other bodies, a body has constant speed. And somehow he assumes that we are working on R3. So now let me propose a kind of a homework, okay? And my homework, you see, I'll ask a question, and you may send me an email in reply. Just imagine that our Earth is covered by ice. And it is exactly a round sphere, okay? Consider a small body on the surface of this Earth. Okay, in this case, position would be a point on the sphere. Now, consider what we would like to call inertial motion in the Newton sense. So we know how to describe this motion. You need to pick up a direction, say like this. You need to pick up a geodesics, and the inertial motion would be motion along geodesics at constant speed. So my question is, first law applicable? So what is this coordinate system? And if there is such coordinate system, why we are not using it? So main problem is here that go with constant speed means that that your acceleration is zero. However, acceleration that we call A is not a temporal. And if we change coordinates, I mean changing only x coordinates, you can go from zero acceleration to non-zero acceleration. So it means moving at a constant speed depends on the choice of coordinate system. So it will be very important to find such coordinate system for the sphere. Okay, so in this way, so from this, so here is my question. Question 1 for audience. Find inertial coordinates on a sphere. Now, let me explain why instead of giving some axioms or formulas, I am drawing a picture. It is because when I give some axioms, you may ask, if there is an object that fulfills these axioms, okay? And you know, in mathematics, people say the following. If you have an example that fulfills the set of axioms, it means that they do not contain contradiction. They may be non-complete. It means that you'll have a set of something that satisfies these axioms, and they will be different, but at least they would not have contradiction. So how do we apply this principle in mathematical physics? We construct a world for which we are sure that it could exist. So everybody understands that we can have a planet that is round-shaped and covered with ice. So it's kind of obvious from the natural point of view. So it is natural to consider such physics. Okay? So this is about the first law. Once again, rotation is omitted and unclear. Okay? But it's an axiom. Now, choice of coordinate system is also unclear. There is a lot of worlds that are curved. And actually, as I will show later, our real physical world is curved. Not only in space-time, but also in space. And we will consider examples of this curvature. Okay? So that's why this first axiom about inertial coordinates is very doubtful. Okay? But let us go on. Okay? Now we come to the second law.
Sorry, Andre, somebody asked questions.
Oh, sorry.
Yes.
You see, it's because I am, you see, it was better to ask. Okay, don't quite understand the question. Let me explain. Is it possible to find such coordinates on the question? Is it possible to find such coordinates on a sphere that, so that would be two of them. I'll call them phi1, phi2. That inertial motion would be phi1 dot is constant, phi2 dot is constant, where inertial motion is the motion along the geodesics. So instead of saying geodesics, I could say meridian. Along the circle with the length 2πr, where r is the Earth radius. So it is the first question. So Mr. Hu, do you understand the question now?
What do you consider coordinate system?
Oh, sorry. Once again, yes. Sorry, Ms. Hu, yes.
For the normal meridian parallels on Earth, does it count as a coordinate system for you?
So it is a coordinate system, but in this coordinate system, the motion doesn't have this form.
Yes, yes. Okay. Yes, I think I get it now. Yeah, I understand.
Okay.
Thank you.
So it is always good to read classical works. Okay. Now let us come to the law number 2. And here in the law number 2, Newton say that bodies are acting on each other by forces. Now, I want to comment on the philosophical origin on these forces. What is force? So, this is philosophical category that was borrowed from the observation of society around a scientist. When he looked at society, he sees that there is a king, okay? And then king orders nobles to do something, say to go to war. King forces nobles to go to war, or knights, whatever. Then knights force farmers to grow some food for them and to build them castles. Then farmers in that force, say, horses to carry them and to help them to dig the ground, do agriculture. So what Newton and all others saw around him in the world, that everybody wants to be in peace. And in order to move somebody from this position of being at peace, now he said inertia, move with constant speed. He thinks that moving with constant speed is also a preferable position. Someone or something has to force somebody, okay? That's what he see around him. And that's why he get this idea. Force actually means violence. You disturb somebody. So bodies disturb other bodies just like people disturb other people. Okay? That's what is inside the concept of force. So without force, things would be at harmony, at peace. Okay? That's why this is very Western concept. I would say that in the end, you will see that this Western concept of forces and violence would be replaced by the Eastern concept of harmony and tendency to harmony. Okay? So this is culturally dependent piece of the theory. Now, theory with harmony, so forces means violent philosophy. And there is another thing that's called extremal action. It's about harmony and cooperation. So this is West and this is East. Okay? But now we explain West. So, okay, there are forces. The law that acceleration equals to force. What does he say about forces? First, forces are vectors. So it is before creation of linear algebra, but Newton assumes.
Andrei, there is a problem with your video.
What is the problem?
We can't see your video.
Okay, so it logged out. Okay.
Okay, now it's good.
Okay, thank you. So forces are vectors. Newton said that if you have forces from there is a notion of adding forces. So forces are vectors and could be added. That's why the configuration space has to be a vector space. Second concept is that if you have body B1, body B2, and body B3, then force acting on B1 equals to the force B1 due to B2 plus a force B1 due to B3. So it's an axiom of adding forces. So I already criticized forces being vectors when I was talking about configuration space, but let us assume for the moment that configuration space has inertial systems, okay? Then we may ask, what can we say about this axiom? I mean, addition of forces. And there is a law number 3. You see, I have to consider them together because after describing them, I will start with counterexamples. So it is called law number 2. So law number 3. It's interesting. He says the F A due to B equals to F B due to A with the minus. But it is only the first part. The second part is that this F is parallel to the line connecting bodies. So two pieces. Okay. So there are two pieces actually here. Let us first try to understand what this means. What is the line connecting bodies? So there is a body number 1. There is a body number 2. What does it mean, the line connecting bodies? If body is not a point. this line or that line. So if we just assume that, say, okay, a body is position of the center of the mass, okay? Plus rotation, but he has no rules about rotation. So his rules are incomplete. So let us try to save the game. Save the game. Let's think that FB1, B2 is parallel to the line connecting centers of mass. Unfortunately, this is not true in real physics. Example. Suppose you have a proton and also say proton and electron. Then center of mass of the second body is somewhere here because electron is very light. Force points in the very different direction. Okay, let it be not electron but neutron. Then center of mass is here, while force is going along this direction. So we cannot save the game. Just no way. So the second law is incomplete for bodies, for solid bodies already, because it ignores rotation. You may consider center of mass here. The third law is ambiguous. We don't know the direction. By the way, would it be no direction? We could violate a conservation of energy. Example, consider two bodies, body 1, body 2. Let us assume that somebody holds these bodies. And there are forces, one acting this way, another acting this way between them. So would there be such a force? Such system would rotate faster and faster. And it's definitely not a system that Newton assumed in his axioms of mechanics. So we have to include this line connecting bodies. However, it's not clear how to draw it. So, from this quick inspection of laws of Newton, you should understand that if you are a mathematician, you cannot accept this construction at all. Just forget about it. Not complete, ambiguous. You see, just unclear. That's why this line connecting bodies is often omitted in the school books. So it is written in the small letters. Or people say that Newton assumed something. Sorry, people. This is an incomplete, ambiguous set of axioms. So now let us try to say Newton's ideas. Okay, so now it's a good time to make a break. Because what I'm going to do now, I'll go to do something to save his ideas, and we will have a, let me see, the clock. We will have like 5 minutes break, okay?